Welcome along, another blurting video, waves and diffraction. I've got the questions you're going to be doing in front of me, so I might refer to those just to make sure I cover everything. I'm going to start with the sort of simplest arrangement required to make an interference pattern on a screen. So if we shine laser light through a double slit on the screen, we will see a set of red spots. These are referred to as fringes. And the reason we're seeing those is because of constructive and destructive superposition. So on a simple level, if two waves combine in a way where they're in phase, we get peak plus peak, we get a super peak. Whereas if we do trough plus trough, get a super trough, that's constructive superposition. But if we do peak plus trough, we get nothing. So the bright spots on the screen, for example, this one in the middle, are caused because the waves from the two slits are in phase, meaning that peak meets peak and trough meets trough. And in that centre bright spot, both sets of waves are travelled the same distance. If we're looking here, that's dark there. The waves from the bottom slit have had to travel further than the waves. The waves from the bottom slit have travelled further than the waves from the top slit. The waves are now out of phase, so our two wave trains are like this. They are out of phase and they will add up to give low amplitude and a dark spot. And that's because these blue waves have travelled half a wavelength further, putting them out of phase. And then we can refer to the path difference as we go through. So this one here will be one wavelength, here 2 wavelengths, here 3 wavelengths. Then the dark spots are half a wavelength, 5/2 wavelengths, which is what I'm trying to write is there, and then that's actually 3/2 wavelengths. Next, I'm going to talk about, this works more easily with a laser, but the two sources have to be coherent. That means that the phase relationship between the two slits has to be constant. They normally would be in phase, but it doesn't matter if they're out of phase, as long as that's a constant relationship. So if we wanted to produce these fringes with a light bulb, we would need initially a coloured filter. So we only have monochromatic light of one wavelength. And then we would go through a single slit to help make the waves more coherent. So our wave fronts are now travelling out like this. Because both wave slits are the same distance from this slit, the waves are arriving in phase, have a constant phase relationship, and then they can spread out and where they overlap, but only where they overlap do we get a diffraction pattern, interference pattern. The reason I'm saying the word diffraction is, so wider waves spread out, and the word we're looking for here is waves diffract through a single slit and spread out, and that effect is strongest when the gap is about 1 wavelength across. In these experiments, actually, the gaps would be many wavelengths across, but we can still get good diffraction even with many wavelengths across. It's only if you go up to thousands of wavelengths across that we wouldn't really get very much diffraction. The next situation I want you to be aware of is the diffraction grating. So our basic setup is the same. We have a beam of laser light, and then we have a diffraction grating, and then we have a screen. And now we're seeing really clear, well-defined spots on the screen. And we label those, we call the middle one the 0th order, or n equals 0. Next pair out are n equals 1. Next pair out are n equals 2. And then we can imagine the light arriving here the diffraction grating has multiple slits, and each ray of light from each adjacent slit, the path difference is one wavelength. So just like before, all our waves are in phase. We get constructive superposition. I didn't do the equation for the double slit pattern, did I? Let's go back to here. Lambda equals WS over D. So D, capital D, is the slit to screen distance. Lambda is the wavelength. S is the distance between the centres of the two slits. And W is the distance between the two bright fringes. Right, back to this one. So this equation is slightly different in form. N lambda equals D sine theta. And N is these orders, which spot we have going out. Lambda is obviously wavelength. And now we're relating to the straight through. So this ray, this line I've drawn is a normal to the grating. Theta is the angle to the bright spot. And obviously there are multiple solutions for each of the bright spots. The things we might need to know are how to find D and how to find the maximum value of N. So D, so if we zoomed in, we would see many, many, many slits, and D is the distance between those slits. The complication is that sometimes this is expressed as, say, 300 lines per millimetre, and that's not D. So how do we find D? Well, 1 millimetre is 10 to the minus 3 metres. And if we divided that into 300 parts, because there are 300 slits, that would be how we would calculate D. We'll see if the iPad can solve it. I bet it can't. And then that's D. I don't know why it didn't give me the answer. I clearly clicked the wrong bit. And then finally, we might get asked a question, either how many spots will be visible, or we might be asked for the highest order. Okay, I've just got a load of nonsense there. So that would be the greatest value of N. So if we want to know the maximum value, this keeps cropping up a lot, so clearly something we need to know. The maximum value that sine theta can have is 1. Actually, it's not the last thing, it's nearly the last thing. So that solves that one. So we've now got N lambda equals D. So N is D over lambda. And we might get some kind of decimal, like 3.8. We would then round down to the nearest whole number because we've said that 3.8 is the max value, but it has to be an integer, so N is 3. But then if we go back to how many spots, well, we're going to have one centre spot plus 6 other spots. There'll be 7 spots in total. Let's see if we click solve there. I don't know where the answer's gone. Never mind. And finally, we need to know what would happen if we use white light. So I'll use the diffraction grating again this time. So I'll just draw. So here's that's the edges of our beam of white light. So in the centre of our screen, the impossible thing to draw, we would see a white spot because all wavelengths peak for N equals 0. And then for N equals 1, we go back to look at the equation. N lambda equals D sine theta. Longer wavelength will give a greater angle. So we will see initially blue light, can't quite do the whole spectrum, going through green light out to red light, and we would see a really well-defined spectrum. When we go out to N equals 2, it starts to get a bit more messy because the orders start to overlap. So I think that you'd see that the the red of n equals 2 would start to merge into the blue of n equals 3. But generally speaking, the kind of the key things for your marks are white central maxima, spectrum on either side, so this would be reproduced on either side, and that spectrum would be the order of that spectrum, the order of those colours is to have blue on the inside and red on the outside. Right, I hope you found that